It is my honor and my pleasure to introduce Maya Gupta in this invited talk session to you all. From what I could find, she was a professor at the University of Washington, and since 2012, she's a principal scientist at Google Research, and more specifically in the Glassbox machine learning R&D team, and also co-founder of a number of companies. She regularly publishes at CPAIOR, NeurIPS, ICML, and these other fantastic venues. And often it is on the topic of learning under constraints, for example, in the context of fairness. And I'm looking forward to hear much more about that from her in this talk.
Thank you. To be clear, I left Google about a year ago, but much of the work I'll talk about today is from around 10 years I spent at Google running a machine learning R&D team with many other wonderful researchers. I think I've got most of the key ones down here. And everything I'll talk about is Google, is public, has been published, so you can find papers, so we won't say anything confidential. And that's one of the things that I loved working about Google, is that they were very good about publishing many of their top technologies and their new ideas. Since then, I am co-founded a new startup called Diderot. We do personalized web recommendations for books and TV shows. We're also using many of these same technologies, so I'll bring a little bit of that perspective in as well. And I'm just excited to talk to you guys. I know everybody's working on constraint optimization type issues, and I feel very passionately about why this is important for the future of machine learning. So excited to tell you guys a bit about that. And let's, well, first of all, we have to figure out how to turn slides here. Okay. We're going to start with an example just to get motivated. And this is a very simple two-dimensional machine learning example. And we're just going to have one goal. We're going to try to predict if a law student will pass the bar. And in the United States, when people go to law school, they have to take a standardized test called the LSAT. So our two features here, one on the y-axis is the LSAT score, and the other is their undergraduate grades in college. So given these two pieces of information that you would know, like when they were 22, are they going to pass the bar after they finish law school and be able admitted to be a lawyer? So we get some information about who's passed the bar and who hasn't, and we train a DNN on this two-dimensional space. And we have about 20,000 training samples in 2 dimensions. So this seems like a very easy problem, plenty of data here. This is kind of big data in microscope. But you'll notice something kind of weird about this model. So these different lines here are telling us the model's confidence that you'll pass the bar. So brighter is, we're more confident if you have a high GPA and a high LSAT. But you'll notice that there's this kind of weird crook here. And in fact, what our DNN has learned is that at some points in this space, if you have a certain GPA or a certain LSAT, increasing one of those others will actually decrease your predicted passing rate. So here you are like this GPA of like 2.7. So you're kind of a middling student, you've got a middling LSAT. And here we're saying that if you had actually gotten better grades, we would lower our predictions for how well you were going to pass the bar. So that just seems frankly wrong, right? This is kind of a strange thing for this model to have picked up, but we fit a model to data. So we shouldn't be surprised if it does some stuff like this. There was nothing to tell it not to do things like this, and DNNs are very flexible, but flexibility is what we want out of modern models. And if we look at the training data, and this is the problem with big data, even when you have big data, so 20,000 training examples in 2 dimensions, I mean, this seems like overkill, right? But it's not big data everywhere. So there's going to be some sparse here because not that many people who are such middling students are even taking the exam anyways. So we do have areas still where the data is sparse, and that's in particular where our model is behaving badly in this way. But this is particularly bad, right? If we, use this to give away scholarships or use this to decide law school admissions, and people looked at this model and they realized it had these problems, people would be up in arms and say this was not fair and this was AI doing the wrong thing, and it would not feel very good to people. So what can we do? Well, I'll talk today about some of the solutions. We can force monotonicity on the model. So this is one of the kinds of constraints that we can force on our machine learning models. And what that will mean is that we'll say for any point that you are in this space, if you get a higher GPA, the model value should go up. Or if you at any point you get a higher LSAT, the model value should go up. And you can see when we train a model with these constraints, again, arbitrarily flexible model, but adding in those monotonicity constraints, we get contours that are much better behaved. And they mostly look the same. And in fact, the test accuracy here is statistically significantly the same. I think actually the one on the right might be slightly better, but basically the same, because the only place the problems are happening is where there's not much data anyways. So you're not really going to see this necessarily as a difference in your test accuracy. But at a high level, this is an important feature about the model that makes people either feel like, oh, I can trust AI, or, oh, look what these strange things that this AI is doing. It doesn't match my intuition or what is fair about a model that's making decisions like this. So what do we mean by monotonicity shape constraint? So our model here is some function f. We'll have two features, x and z. And we're saying that if we want it to be monotonic in GPA, then if I have any 2 points with the same LSAT score, the same x, but one has higher GPA, then yeah, if there's a higher GPA, then it has to be that the model is getting bigger in that direction. So basically these green arrows have to be true anywhere in the space. And if this model is continuous, we can just say it has a positive first derivative or a positive differential in that direction. So that's one example of the kind of constraint that we can add into these models that in this case will really change the fairness of the model and the perceived trustworthiness of the model. And you can read more about this example and some other examples of this sort in our AI stats paper on deontological ethics by monotonicity shape constraints. I know if you haven't done a lot of fairness, the word deontological ethics sounds like some fancy ethics, but actually it's the most common ethics. It's the rule-based ones, like getting a higher GPA shouldn't hurt you, or the first person there should be served first come, first served. These kind of rule-based ethics are all just deontological ethics, and you can impose them often with these kind of shape constraints. Okay, so more generally, and let's see if I can find my screen here better. More generally, we're talking about taking noisy training data, and instead of just training and getting some ML, we want to impose upon the training some additional model constraints, and those model constraints ideally will reflect the domain knowledge and policies we have about that problem. So in this case, we know that, hey, better GPA shouldn't hurt you, better test score shouldn't hurt you, and we can reflect that in, for example, monotonicity shape constraints. And the goal here is not just to get better test accuracy, because that's not really the real world goal either, but to get machine learning that people are happy with, that people trust, that people believe in, that actually does what you want the machine learning to do, which may or may not be fully captured by test accuracy. And I'll talk today about the two types of useful model constraints. There's two classes that our team saw at Google over and over again. And I was a little surprised. I've got this gray Venn diagram here. There's probably other classes of useful constraints, but we were surprised how we talked to a product team, and often whatever they wanted really did fit into one of these two kinds of constraints. And we'll show that these are sort of mathematically different sets of constraints. On the left are shape constraints. These are constraints about the shape of the model itself. So the very simplest one is probably linearity, which just tells you the model has to be linear. I won't talk about that today because it's very boring. But for example, we just talked about monotonicity. You can have an arbitrarily complicated model, but it has to be always going up in one direction. And we'll talk about diminishing returns, and then a couple multidimensional shape constraints as well. And then we'll talk about rate constraints. And rate constraints are different because they're not constraining the shape of the model, they're constraining the behavior of the model. They're constraining the statistics of the model and how it actually acts in practice. And in sort of fairness terms, on the left, we have these sort of rule-based deontological type fairness metrics. And on the right, we have more like equal utility or egalitarian type metrics that look at the outcome and say, what does the model actually do in data? And we'll talk about that. So first, we'll dive into some bit more detail on shape constraints, a few more examples, and then we'll switch over. Okay, so just going to talk about domain knowledge and policies, and talk about some more examples on the kind of domain knowledge and policies that you can impose via shape constraints on the model. So in this this next example that I've simplified a little bit, let's say that you're trying to rank coffee shops. Maybe you run, a global search engine that helps people find local businesses. Who knows? So you might be trying to help people rank coffee shops. And one of your features about each business or coffee shop is how far it is away from the user. And so you might get some training data, and this is just toy data here that tells you how happy people are to walk so far or to go so far for coffee. And maybe your data is a bit noisy, and so you fit a DNN and you get something that looks like this. And again, this seems a bit weird, right? We don't really believe that people are less happy at 1 kilometer and suddenly happier to walk 3 kilometers. This is just the fact that we fit too flexible a model and didn't have enough data. So we can, again, constrain things to be monotonic by adding those shape constraints on the model, and our fit probably will work just as similarly, or not quite as well on training data, but just as well on test data. And that's already looking a little bit better. Now here we might go even a step further and say, well, look, we know something about distance. We know that distance has diminishing returns And that if you have to go, the difference between 1 kilometer and 2 kilometers is not is bigger than the distance between 5 kilometers and 6 kilometers. Once you're going 5 kilometers, you're okay with going 6 kilometers. So there's a diminishing returns effect. And so we might also impose a diminishing returns effect on the model in this with respect to this feature, which we could do by forcing the model to also have a convex shape. And this is the kind of curve fit that we would get then. And then we would have sort of brought in this additional prior on how distance should make sense. Okay, there's a NIPS paper that will tell you a little bit more about that. So how do we do these types of shape constraints? And this will generally be true even of the multidimensional ones. There are various ways that you can do it, but this is the way that we found really was very efficient and very flexible. And that's to use interpolated lookup tables. And in 1D, all an interpolated lookup table is a piecewise linear function. And if you're old like me, you might remember in the back of your textbook, we would have these tables back before we had, computers and stuff. And if you wanted to know what the sine or cosine or logarithm was, you'd go and look up in these lookup tables, because that's how we stored approximations for functions. And so all we're doing here is we're also storing approximations for functions by a grid of values, and we're learning those values. So the model parameters are indeed the values. So for example, here, this one-dimensional piecewise linear function, we might say has 8 parameters. The output at these different input x values will be our parameters, and anything that comes in between will just interpolate from the 2 nearest parameters. So learning a piecewise linear function, super easy. If you care about squared error, you can do it with the pool adjacent violator algorithm. But the really nice thing about this kind of setup and these interpolated lookup tables is that in order to constrain them to be monotonic, we just need to make sure that the parameter values are increasing as we go in the direction that we want to be monotonic. And so that means we just need a nice little linear inequality constraint. And in general, we can then form our training problem for whatever your losses. If you're not squared error, you can't use pool adjacent violators, but you can have whatever function class you want here in 1D space. And you could say, okay, I want to minimize the model parameters such that the sum over training examples of whatever loss you care about is good. And I have this constraint that these linear inequalities are happening on my model parameters, that they're going up. So you just get a nice matrix of linear inequality constraints, and lots of great ways to solve those. What's interesting about these problems is that as we move to bigger models, the number of constraints here may easily be on the order of millions. So we have to do some special handling to do a good job of that. But we'll talk about that a little bit later on how to decompose that. Okay, so this is a great, simple, hopefully familiar way to express a monotonic function in 1 dimension. Of course, we don't really only want 1-dimensional functions. We need to do multidimensional functions. So how are we going to get there? Well, the first sort of step we can take towards that is just a generalized additive model, where if we have multiple inputs, we can learn a piecewise linear function for each input on it that only acts on its own, and then we could sum them. So this is a very old style of model. You can see Tibshani and Hasty's book on generalized additive models. People like them because they are pretty easy to interpret and explain, but they're not arbitrarily flexible. And today in machine learning, you have to bring arbitrarily flexible models to the table. It's because there's so much data and people want that accuracy. So instead of doing this, we're going to build on this idea. We're going to keep that first layer of taking each of the inputs and separately transforming them with their own piecewise linear function. But instead of then just taking a linear sum, we're going to put more flexibility to the later layers. So just like deep neural networks have many layers, we're going to think about this as just a simple calibration layer, and then more flexibility in our later layers that's going to fuse our inputs jointly to get arbitrary flexibility. But if we didn't care about the shape constraints, we could just use DNNs. But if we want shape constraints, we need to somehow do that in a way that still imposes some shape constraints like monotonicity. So there's a little bit of trick there. So what are we going to do? We're just going to take the same idea we talked about before, and we're going to do it in a multidimensional way. So we'll use multidimensional interpolated lookup tables. So here's a simple one on 2 dimensions. This lookup table has 10 parameters, 2 by 5 grid. And if you come in anywhere in this space, you'd find the 2 to the D or 4 parameters surrounding you, and you'd linearly interpolate from those, which will, linear interpolation gives you a nonlinear function because you are interpolating 4 parameters. And if you put more of these grid points down, you can express whatever complicated nonlinear function you want. So you get the arbitrarily flexibility here, but you're doing so at the sort of exponential scaling of parameters in high dimensions. So you can see that you get all the flexibility you want, but it's going to be a little costly in terms of parameters if we're not careful. But again, you can see that now if I want monotonicity, if I make sure that all my parameter values are increasing in the up direction, I will get a monotonic model in the up direction. If my parameter values are always increasing left to right, then I will get a model that is monotonic left to right. It's very easy to prove. And so it's easy to check if a model of this type you have is in fact monotonic. And if you want to constrain it, you're again going to have just linear inequality constraints, which is nice. So we could have just used a multidimensional lookup table as our whole model, but by having two layers, we get a more efficient use of our parameters. So if we just have two inputs, each of them is coming in and being transformed by its own piecewise linear function. That's that sort of calibration layer like you would find in a generalized additive model. And then in a second layer, we're going to do the multidimensional fusing, which can be more efficient. And so we end up having to use fewer parameters. So here's an example of a very simple function like this, two-layer function. You can see there's kind of a lot of flexibility to this function, but it hardly has any parameters. And you end up with these smooth functions because you're linear interpolating each thing, and you end up being able to enable shape constraints because as long as they're enabled at each layer, they'll be enabled for the whole function. So this function is monotonic in this direction. It's not monotonic in the other direction because that's what we imposed. Okay, and you can just blow this up and make these sort of deep lattice networks that have as many layers as you like. And so you might have some inputs that you say these inputs have to have a monotonic impact. So if I'm ranking coffee shops, maybe how far they are, further is bad, maybe coffee quality is good, maybe, star rating is good. And then maybe there's some non-monotonic inputs like the brand name or something. So you have your various inputs, you've divvied them up into which ones should have a positive effect on the model score, which ones you're not really sure. And then you can have these piecewise linear function layers. You can have just linear layers, just like in a neural net. And you can have these multidimensional lattice layers. Here I've shown using an ensemble of them in order to be able to handle more of them. And so you can build very large models on an arbitrary number of inputs. Here I'm just showing 7 inputs because it's hard to show too many inputs on one slide, but build models with thousands of inputs this way and everything works nicely. And as long as every layer is monotonic or every layer satisfies your shape constraints, then the composition will satisfy your monotonicity shape constraints. For your other shape constraints, you have to be more careful because the composition will not necessarily be sufficient. If you have each layer being convex, the composition may not be sufficient to just be convex. So you have to be a little more careful about that. Okay, and the beautiful thing about these lookup tables, they're called lattice models, interpolated lookup tables, and putting these in layers is that because each layer just requires some parameters to have linear inequality constraints, we end up with these very nice training problems that just have these linear inequality constraints to solve. Now, we built toolboxes, computational toolboxes to solve these about 5 times over my 10 years at Google, a couple times in C++, a couple times in TensorFlow, and once in a compiled optimization language. And every time we did it, we tried different ways of handling these constraints because you end up with, in many practical models, literally on the order of 1 million constraints. But in the TensorFlow Lattice library, which is available publicly, we do use just a batch stochastic gradient descent over the training examples and then Dijkstra projections to satisfy the monotonicity constraints. And you can dig into that. Is that the best way to do things? Not necessarily, but it was the way that works best with the TensorFlow tools. Because in TensorFlow, you're trying to use the underlying primitives that are sort of well optimized for TensorFlow. And this was what we found worked best. We had an earlier version that used a consensus-based ADMM, and it was really beautiful, and it was in some ways a much more efficient constraint handling, but it required a bunch of specialized C++ tools on top of the usual TensorFlow operators. And so as TensorFlow evolved, it was very hard to maintain. And so we went to something that was not as satisfying, not quite as satisfying from how we handled the constraints, but one that was easier to maintain as the software library evolved because it was using more native operators. So some interesting complexities there about really making things work in practice. Okay, so we talked about monotonicity and diminishing returns. I want to talk about a couple multidimensional shape constraints that we found very useful. One is product team would come to us and say, look, we've got this model and we don't have very much data to train it, but we know that a particular feature is more important than another feature. And that should really be showing up in the model. And, we're not gonna be able to launch the thing unless we can guarantee that the model's doing the right thing with respect to this. So for example, if you have some sort of time series model, you can know, or you might decide or impose that the most recent data, really, I should trust it more, and I want that to weigh more in the model, however that means, than older data. Similarly, if you have something like a web store and you're tracking how well the web store is doing, if people are actually buying something, that's more important than if they just do views, right? You might have 0 buys and you might have lots of views, but you'd still like any one buy to be more valuable to the model than any one view. And just in general, in American English, we say that birds in the hand are worth more than birds in the bush. So anytime you have some features like this, you may have a dominance relationship that you know a priori, and that you might like the model to respect, even though the model is going to go off and train on noisy data. And if you have a linear model, this is very easy, right? You just look at the linear coefficients for the 2 features and you're comfortable, you know everything is working. But when you have these big nonlinear models with lots of layers and lots of flexibility, it's much harder to check if these relationships hold and to impose them. So what do we mean by this? Well, if we look at that in a continuous space, we're basically saying that anytime this one feature X1 changes, it should have a bigger impact on the model F than if this other feature X2 changes. So they should both have, say, a positive impact, and one of them should be a bigger impact. So here we're sort of saying the model should take a bigger step in model space in this direction and that direction. And that's also like saying in the 2-dimensional X1, X2 space that it should be monotonic along this line, as well as along the horizontal and vertical axis. And as I said, in a linear model, all you're saying is I want the coefficient on one to be bigger than the other. But to get arbitrarily flexibility, we found we need to use these lattice models, these interpolated lookup table models again. Okay, so that's dominance. A different idea that we actually saw more useful in practice, because so many people have this problem and it's a harder one to machine learn, is when people know that 2 features are complements. I studied economics, where the classic example of complements, at least in America, is guns and ammo. You know, your guns are not very useful if you don't have ammunition, and it's no good to have a round of bullets if you don't have a gun. Yes, I studied economics in Texas. We talk about vaccine doses and nurses. If you don't have someone to deliver the vaccine dose may not be that useful. Your cashiers need cash registers. And in more of an internet setting, we worry about things like click-through rate and the number of impressions. So you might have an 80% click-through rate, but if that's based on only 5 impressions and there were 4 clicks, that's not as impressive as if you've seen 800 clicks on 1,000 impressions, right? So often people will just take the fraction and they'll run off with click-through rate, but if we also know the number of impressions, we like to take that into account. So mathematically, what we're saying here is that we'd like to have a constraint where the second derivative of the model with respect to the 2 different features is positive. And so pictorially, this looks in practice, so this would often look like you'd have some sort of feature that was a rating feature. Again, like say maybe we're Amazon and we're rating books. So we have customer reviews that tell us, you know, how good the book is. And so we're positive in rating, right? We'd like to have things with higher ratings, but we maybe also have a feature that tells us the rater confidence. And so if the rater confidence is low, because maybe we just have a few ratings, then the average star rating or the rating score, it doesn't matter if it's very positive or very negative. We can't trust that very much because we just don't have much confidence in the ratings. Maybe there's just not very many of them. When we have high rater confidence, then a positive score is really great positive information and a negative rating is really great negative information, right? You've all seen, you go to look at a restaurant review and it says that there's terrible 2-star rating. And then you find out it was just one guy who had a bad experience. Well, that's, you know, over here, you shouldn't take that too seriously. But if you have 1,000 people with bad experiences, you start to realize that that should be more important. So these kind of feature relationships that you may know, you can start to capture and impose by these kind of constraints that say that they must be complements. And this is just a continuous version of submodularity. Here's another sort of set of examples of where this is useful. Anytime you have a measurement and you say, look, my model score should be positive in the measurement. This measurement sort of correlates with whatever I'm trying to machine learn. And then you have another feature that tells you the precision or the noisiness of that measurement. If the measurement is not very precise, you can't trust the measurement very much. And so your model score should not change very much depending on the measurement precision. But if you have a very precise measurement, then you can be more confident and you can have a wider swing or a higher derivative, if you will, of your measurement of your model score. Okay. So yeah, so these are all some different kinds of shape constraints, and we find that they are useful both for regularization but even more so just to have trustworthy models. Like in that first example about the law school, you wouldn't have seen the difference in test accuracy because there weren't enough test samples out there, but it makes a big difference between whether the model is something that you say, yes, I understand what this model is doing. You can trust that it's doing something sensible. It's not going to make you mad versus we don't really know what this AI is. We poured some data in, we stirred. I don't know. I've got this AI. It seems to be 80% correct. Let's trust. And a lot of this also comes down to interpretability. If you need to explain models, being able to say, well, this is a model where if your coffee shop is further away, it's going to get a lower score. If everything else about the coffee shop is the same, we find this has helped a lot with explainability and also with debuggability, because when you have these kinds of constraints, your model tends to fail in sort of very predictable ways and ways that you can think about because you understand the constraints that the model has to satisfy. Okay, bunch of papers here. This JMLR paper from 2016 gets into the basics of these interpolated lookup tables. And another useful one is multidimensional shape constraints, and also for set functions is pretty interesting. Okay, so that was a sort of shape constraints. And now we're going to talk about this whole other set of constraints that we found, again, very useful for product teams and what they actually want to do with machine learning that I'll call rate constraints. So here's our very first example, which again, hopefully feels familiar. This is also called the Neyman Pearson problem. I've got a classifier, and in this part of the talk, I'll really just talk about classifiers, and you can imagine them all to be binary classifiers, but things can be extended. So let's say I've got a classifier. I want to minimize the classification errors just like I normally do. So that's my standard empirical risk minimization. And now I might have a constraint that says, look, the recall has to be greater than 70%. But I might have a different problem where I want to do something different. So anyways, this was the first example of rate constraint. Here I might have a million training examples, and maybe those million or billion training examples are very noisy. Maybe they're coming from clicks. So I want my classifier to do well in all those training examples, but I may also have some hand labeled examples that maybe are capturing some policy or capturing what I really care about. For example, if we are looking at ranking news items or something, the training examples some of them might be clickbaity. So people might be clicking on things they really shouldn't even be clicking on, and not that they even want for news, but it was just flashy. We call it the bikini effect. You see the bikini, you go off and click. Whereas I might have some hand labeled training examples where someone has gone through and said, look, this really was the right thing to do. And I don't have enough of them to train my whole model. But if I put a constraint on my model that says I've got to get at least a certain accuracy on those hand labeled examples, then it's going to steer the whole classifier to do the right thing on the million training examples and to ignore more of the noise, because it knows what it's looking for. It's looking for the stuff that the hand labeled examples are right on. So this is again an example of a rate constraint. And here's a different example. This one is very important in terms of actually launching things. So often in production, you already have a production classifier. There's already a classifier out there in the real world. And these classifiers are often in long pipelines of decision logic. It's not that there's just one classifier that does everything. An output that you see on the internet may actually be the product of 5 or 10 or dozens of different classifiers that have acted on different data. So for any one of those classifiers, you've already got a production classifier, and now you're training a new classifier. Maybe you've got updated training data, maybe you got new features, and you may want it to have low churn. That is, you may want the classification decisions to not differ too much from the production classifier. And in this case, we're going to say they can't differ more than 2%. And you might say, well, isn't that bad? I don't want to limit my accuracy gain. But often you're making a change that's maybe going to have a 0.5, maybe a 0.3% accuracy gain. But in order to get a 0.3 or 0.5% accuracy gain, if you do nothing, an unconstrained classifier might change 10% of the decisions. And that 10% of decision change is going to cause all sorts of churn and instability in your system. And it's going to make it hard to measure whether or not it's really a good classifier or not. So in order to actually get things launched, we often found that we needed to have low churn or classifiers that looked a lot like the production classifier and sort of only were better in a few places and didn't make a lot of just change decisions just to change decisions. Okay. So here's I think my fourth example, and then we'll take a higher look. This is the kind of fairness example that we see, and you'll see a lot of this kind of discussion in the machine learning fairness literature. But it's an even broader question than just fairness. The issue here is that we might have some data, and we're trying to train a classifier that will work all over the world. But we might have a slice of data, and we'll call one slice India, and we'll call the other slice US. And we might need, for whatever reason, that the classifier is working roughly equally well on those different slices. So whether that's about being fair to India versus US, whether that's about being fair to the product teams that are working on India versus US, whether that's just a launch criteria someone has imposed, we may want this to be true, that the classifier is working roughly equally well on different slices of data. And then people will often say, oh, well, if I have one of these constraints, can't I just change it into a penalty and treat it like a Lagrange and everything's good? Why write these things as constraints? But we found again and again that it was easier for people to think about things if they could write clean constraints than if they had to put on some arbitrary penalty. The weight on the penalty would be very hard to set. These kind of numbers here, it's more semantically meaningful what's going on here. And then also that once you get started with this, you often have multiple constraints and you want to satisfy all these things at once. And if you want the accuracy in India to be close to the accuracy in the US, you probably want that for 100 other countries as well. And so you start to have quite a few of these constraints. And each of these constraints is expensive to compute. But all of these mathematically and from an algorithmic point of view look very similar. And that's why we call them all rate constraints. And by rate constraints, I just mean that we can look at the positive rate of the classifier in a data set D. So looking over all the training examples in that data set D, what's the indicator? It's either you got it correct or not, or whether, well, the positive rate is whether you classified it positively or not. So indicator on whether f of x, the model is greater than or equal to 0. And the negative rate, the indicator of how many training examples or examples in set D you classified as negative. So for example, if you wanted the recall to be at least 70%, that's a constraint that says the positive rate on the data set where the training examples were labeled 1, that is the model's positive rate on things that truly were positive, should be greater than or equal to 0.7. And so you can see that you end up with these constraints that have these sums of indicators in them. And more generally, we end up with constraints that look like some set of sums over some set of positive rates on different data sets. These might be slices like the India data set examples or the US examples, and some linear combination of the negative rates on some other data sets have to be constrained with some numbers. So this is sort of your general formulation. And so if we look at sort of the full problem, then this top line is just your empirical risk minimization problem. And here I'm not going to restrict your function class. So you can do this with linear models, you can do this with DNNs, you can do this with lattice models. So you just got your normal empirical risk minimization over some initial training set D0. You want to minimize some loss. You want to have a regularizer on the model parameters. That's great. And what we've added here are these rate constraints that would do all those types of things that we talked about: minimize churn, make sure your accuracy was good across the slices, get things like recall, etc. And the problem, though, is that we have these constraints that are written as sums of indicators. So you may be foreseeing the algorithmic problems here. And we can just sort of more generally talk about those computational problems, abstract that out to saying you've got some G0 of theta, and we've got some GI of theta constraints, and we might have M of them that we want to satisfy. So you're thinking, okay, let's just do a Lagrangian. It's a good solution. So we do the Lagrangian, we get this sort of two-player game where we have a model player who's trying to minimize the Lagrangian with respect to the model parameters theta, and we have a constraint player that's trying to maximize the Lagrangian with respect to the lambda. So that all sounds good, but as we saw, the rate constraints are these sums of indicators. So these constraints are really kind of nasty. They're not differential. They're not convex. We're not going to get good theory out of this. So we need to do something a little more careful. So a standard thing to do in machine learning with empirical risk minimization is you take your indicators and you just do a hinge relaxation. You just replace any time you see an indicator with a hinge, right? It gives you something like this. Very standard thing to do. Well, when we do that with a constraint problem with the hinges, it's worse than when we do it with a loss, is what we found. So Iban et al., another team at Google, did something similar to this in 2017, where they said, let's just relax the constraints. Instead of sums of indicators, we'll make them sums of the hinge loss. And then we can just do a subgradient on the thetas and a subgradient on the lambdas, because now we can take these differentials because we made things the hinge loss, so everything's smooth. But you end up with these constraints that are very, very relaxed. And so you're sort of over constraining your problem. and you already are a little unhappy that you had to constrain things at all, right? If you want to show off your great test accuracy, you don't necessarily want to be constraining things. And so now if you do the hinge loss, you end up with an even smaller constraint set. And so this turned out to be too conservative. So our solution was to change this into a non-zero sum game. So we'll define two different sort of Lagrangians here, one with respect to the theta parameters and one with respect to the lambda. With respect to the theta parameters, we're going to have to relax the constraints. But with respect to the lambda parameters, we don't actually need to relax the constraints because it doesn't care with respect to lambda. So that lets us have two different sort of players, or one has to minimize with respect to relaxations and the other doesn't need the relaxations. As you may realize, we've now thrown away our hope for a Nash equilibrium. We came up with a story about a different kind of equilibrium that you can have, a semi-coarse correlated equilibrium. And the other thing I would note here is that if you have m of these constraints, you end up with what ideally is a stochastic solution. So instead of saying I end up with one classifier, you'll end up with m classifiers and a distribution over the m classifiers, and you really want to sort of be randomly drawing one of these m classifiers. In practice, do we really do that? No, probably usually we just find the best fit classifier to the stochastic solutions. But theoretically, there's a lot of richness here, and it's kind of interesting what happens. Okay, here's a few papers we wrote about all that. The most useful one, probably at least to start, is the JMLR 2020 paper, which is both talks a lot about these real world needs, about churn, about fairness, and what kind of constraints you might want to write, as well as that sort of non-zero sum two-player game approach. And of course, there's a lot of related work computationally as well, so it covers a lot of that related work, some of which you might already know as well. And there is an open source library that we put out at Google as well for that, called TensorFlow Constraint Optimization. This one, I'm not sure if it's as perfectly well maintained. The TensorFlow lattice for shape constraints is very well maintained. This one, maybe a little bit more research grade code. Okay, so bumping back out, we've now talked about these sort of two very different types of model constraints, but mathematically, the shape constraints are all sort of things about, if it was continuous, they'd be constraints on the derivative of the model. We found that we could solve them with these lookup table type functions, and very useful in practice. The rate constraints, very different. Again, these are about statistical goals. And here, everything is mathematically sort of the same for a wide variety of problems that you might want to solve. And as we sort of get into a conclusion here, I just want to really emphasize that in academia and when I was a professor, you just sort of care about your accuracy on a test set, and that's just not really enough in the real world, and it's increasingly not enough. And part of the problem there is that that test set is always some old labeled training examples. But what you really care about is a bunch of stuff, one of which, even if you care just about test accuracy, is test accuracy on fresh labeled examples and the future of how well this model is going to do, which is never quite IID. And especially with internet stuff, everything is always moving very fast on the internet. Your users are changing, your inputs are changing, the fashions are changing, and so you don't have IID. And so you need more regularization than your old test set accuracy would tell you. And constraints can help you get better and more regularization that's sort of meaningful. And because you want accuracy on fresh labeled examples, that means that you're often going out and getting a new test set to decide whether to launch this, a new fresh test set. But that means that you're going to have a much smaller test set. So you may have trained your model on 1 billion samples, but you may only have a couple hundred samples to test it on. And now you need to prove it's statistically significantly better and safe on a couple hundred examples. And that's where that low churn becomes really important, because if the classifier is just changing a bunch of decisions, it becomes very hard to statistically significantly improve on a small data set that it's actually better. So you have to care about the low churn. Another thing I'll emphasize about the real world machine learning is that when you change a model, you often have to be careful not to hurt any stakeholders. And those stakeholders might be users, they might be other engineers, they might be other product teams. So for example, if you've got a worldwide classifier, you can't go around saying, well, I got these huge gains for America, but the classifier now doesn't work as well for India. Even if that's overall better in your aggregate test accuracy, you're going to make some people very unhappy who've been working hard to make the model work well in India, and you may not be able to launch. So this is also about making sure that all your slices are working at least decently well. And that's sort of one fairness metric. Again, there's a large literature on machine learning fairness. How it translates into reality is complicated because often you don't have the sort of demographic information that you might want. So you have proxies for this, and what does it really mean to be fair? There's a lot of complexity here. I'll send you to the papers where we can discuss, but often these things will look like, are the outcomes similar? Is accuracy within some bound? Are people getting a similar experience from your model? And then lastly, and this gets back to that LSAT example that we started with, when you deploy a machine learning model, you want to be confident that nothing embarrassing is going to happen. So even if your test accuracy is great, if you're worried that in the dark recesses of the input space, someone's going to see something that is making these embarrassing decisions, like that they're getting penalized for higher GPA, you can get PR disasters, and you can get a lot of bad press and, you know, just people losing confidence in your product. So this is much further than just having a test accuracy. It's having these constraints that say, look, I know my model is acting reasonably, I can prove it, and be safe. Okay, so we've talked about a bunch of different model constraints and how you can grab different kinds of domain knowledge and policies, put those into the model constraints, put those into the training, and hopefully get machine learning that does what you want. As I said, this was sort of reflecting a bunch of work with dozens of product groups at Google, but I think there's a lot more and even different kinds of product model constraints than I talked about that maybe I just don't know about. So excited to hear what you guys have to say about all that. And if you want to find any of those papers, you can find them on my website at mygupta.org. Thank you.
All right, thank you very much, Maya. That's a very interesting talk and a nice overview. So now we can have questions. So as usual, you can raise your hand virtually or physically in Vienna then. Just checking how I can monitor that. All right, let me start off with the first question. So it's about the general nature of constraints versus regularization. So in this community, we're very much fond of constraints, and we believe that adding constraints is a useful manner, and it gives you guarantees and so forth. But it seems that a common paradigm in machine learning at this point is to simply treat it as a regularizer, add it to your loss function, and be done with it. So you touched a bit on this, where you looked at the Lagrange relaxation. You argued that setting parameters is difficult. So have you walked on this line as well? And what can you share about? And so we're glad to see that you're feeling positive about constraints. But can you share a bit more about that? And
yeah, I mean, I think the problem is that when you're in academia, you're often worrying about like one small problem, right? You're focused on something, and so you'll talk about one constraint. And if you have just like one constraint like this, then it's not so bad to bring it up into Lagrangian and try to deal with it as a penalty. But in practice, once you start having constraints, you often want multiple constraints. And so once you have multiple constraints, if you had tried to specify these with penalties, it would just be a mess because the relative weight on those different penalties is going to change depending on the other constraints. And so you know, we've tried it, but it's a disaster. You can't have multiple constraints, and then someone puts in maybe this recall constraint, and someone next launch wants to have this constraint hold. But if they put it in as a penalty, it just doesn't, you know, the penalties have to change. So I don't think that the penalty thought model or paradigm works well when you have multiple constraints. Even when you only have one constraint, it's much easier to write the constraint in terms of a constraint rather than in terms of a penalty, because again, you have to kind of decide, well, how much do I penalize the loss versus what you're calling a regularizer, and which I'll call a penalty. To me, a regularizer is anything that doesn't just improve the training accuracy. So I consider constraints as part of a regularization strategy. And I think what you were talking about as well, but you can have penalties on my classification problem. Do I have a good example of this? So yeah, here we are saying, okay, I've got a loss that I'm minimizing, and I maybe have some penalties, R theta. And yes, you can do all sorts of things there, but it becomes harder and harder to specify in a semantically meaningful way what those correct penalties are. And then the multiple ones you have, not so good. We do talk, I think we have a full paragraph or two basically making these same points in this JMLR paper. So if you need some backup from a paper that comes from Google explaining why constraints are better, it's in there. But yeah, been there, seen that. I definitely don't like the penalty approach. Under the hood, sure, you're going to go and often do Lagrangians and non-zero sum Lagrangians or whatever, but that's a matter of solving the problems, not a matter of how you specify the problem to communicate with the engineers and the people. And I think this is the other thing that people don't realize so well, is that when you are, let's see if I can find a better picture for this, this picture here, when you are in academia, you are dealing with a bunch of people who all understand everything. So in academia, you can write very mathematical statements and everything is fine. But when you are in a production environment or a corporate environment, these domain knowledge and policies have to be communicable to a wider audience of people who do not understand the math. And so how domain knowledge and policies have to be sort of simple, and people have to say, well, this is what I want. You know, I want recall, or I want that the model works equally well for India and the US. And then you have to translate that into some model constraints in an easy way and into the math. But you can't expect people to be functioning at the math level. It just doesn't work. And this is also on interpretability. The biggest problem we would see with like NERP's papers on interpretability and stuff is they'll come with these interpretability ideas that make sense to other machine learning people, but are too hard to explain to product engineers or managers or vice presidents. You need stuff that's easier to put into normal words in order to be reaching that level of explainability. And of course, there's a spectrum here. When you're debugging, maybe having some of that stuff that is more mathematical is fine, but just that there is also a lot of room in terms of explainability, debuggability, and interpretability for a less complicated audience and making sure that they can understand things.
All right, thanks. Yeah, that's very clear. So let's have a look at the questions again. Where's the participants? Ah, yeah, okay, I see 3 hands. So I'll just follow the order here on my screen. So that's Mikael.
Yeah, so thanks for a really interesting talk. And I was wondering, if I'm a casual user of machine learning, so I'm not really interested in what happens in this black box, do you see any future where we can have these shape constraints and rate constraints easily accessible? Like if I just want to train a small neural network that does something, and obviously these constraints are super useful for any kind of simple model that you want to train. So do you think it's possible to have it available in an easy to specify manner, or do you have to really understand it?
We've tried. I can't promise we've been 100% successful, but there's these couple open source libraries. TensorFlow Lattice tries to be pretty easy to use, but you're already assuming that someone knows how to use TensorFlow in order to use that. The tutorials will sort of walk you through that.
Yeah. Assume I can use Keras. Yeah. You
can use Keras models. Yeah, exactly. Yeah. So I don't know how casual a user you claim to be, but at that point, yeah, you can use things for the shape constraints. For the rate constraints, frankly, it's harder. So the shape constraints, we've done more research. We've used more in the real world. And so we have a better language and better tutorials for the shape constraints in those open source public TensorFlow libraries. For rate constraints, there's just more caveats. It sounds really good to state these rate constraints, but in practice, they're statistical and they're mushy. So let me give you an example of that. You might ask that the accuracy in India is at least 80% of whatever accuracy you're getting in the US, but it may be very hard to achieve that. Maybe the problem in India is just really, really hard. And so in order to achieve this, you might actually really decrease the accuracy in the US in order to get this, right? This doesn't float all boats. Your classifier can only do what it can do. And you might even end up with a degenerate classifier. So there's just a lot more of these sort of statistical gotchas that happen with these kind of rate constraint problems. And you also have to be careful. Maybe it holds on your training data and you get this to hold on the training data, but then you go and grab a new set of test samples. And because this was a statistical constraint, it may not generalize. You may not satisfy this constraint on the test samples in the same way that your training accuracy will not be the same as your test accuracy. So there's a lot more gotchas in the constraint optimization. So while we've tried to make those tools user-friendly, they're just sort of by nature not as user friendly. You know, it's easy for a VP to say, I want this to work equally well in all countries. It's much harder to be like, what do you really mean about that? What can we really do? What can we really promise and guarantee?
Yeah, that's a very, very good point. Thanks.
All right, thank you. So I see Peter next in my list.
You started to talk about it, but I'm wondering how often the constraints hold, or do you have any idea about that?
Yeah, I would say most problems we look at, the constraints hold in part because people are setting the constraints such that they hold. So sometimes you'll get constraints like this and they're just sort of safety checks. But often the reason that people are adding in constraints is because they are right and because it is going wrong, or they, you know, it's subject to going wrong. And things like the monotonicity constraints, you know, they often don't hold even when you have lots of data, just because the space will be weird and there's noise. And so especially the more flexible model you get, the more room there is for these shape constraints to not hold. And so again, you might have in a practical model 1 million of these constraints to get a really monotonic model, and maybe, you know, 100 or so of them are not really holding, but it's unlikely that 100% of them are holding with real true noisy data.
Okay, yeah, but so they mainly hold, I guess, is the feeling.
With the shape constraints, they mainly hold.
Yeah,
yeah,
so
I
you're
mean, if
saying
you have like
100 out of, I don't know, 10,000, right?
So I have a good analysis of that. I'm trying to think if we have. It can be a lot worse or it can be a lot better depending on how noisy your training data and how right you are about your assumptions. These rate constraints also, you know, depending how much slack you give yourself, maybe this is an easy constraint you put in, maybe it's a hard constraint. These like churn constraints where you're trying to say, I don't want it to be too different from a previous classifier, those almost always hold, because just the nature of stochastic gradient descent is that you can have two very classifiers that act equally well that have a lot of change decisions. So those usually quite a bit holds. So I would say in practice, we found most constraints were active, at least in some parts of the space.
Okay, thanks.
All right, so Jochen.
Yeah, so a very quick question concerning this Dijkstra projection that you mentioned in connection with the TensorFlow lattice. So I didn't quite get what exactly you do there and how you're using this Dijkstra projection. So this means that you kind of change the model, right? You apply some reshaping operation to your original DNN or whatever model. Yeah, so you're using lattice models here. Is that correct, or?
Yeah, so we're using these interpolated lookup table models. And so we'll do a batch SGD step. So we'll take, you know, 100 training examples and we'll look at this loss over those 100 training examples, and we'll apply that gradient to the model parameters. And then we go and check, did we destroy the monotonicity? And then we'll project it back onto the monotonic set using just sort of the Dijkstra's algorithm. And I think we get away with like either just 1 step or 10 steps. So we're not necessarily every time projecting all the way back to the monotonic constraint, because you're going to do this many times because you're doing this batch SGD. So you don't always, you know, you don't always have to be feasible. You just need to be feasible at the end. So you just keep kind of bringing it back towards the monotonic set, towards the feasible constraint set.
I see.
And I believe that code is all public, so you could look at exactly what we did in terms of details there as well.
Thank you.
I still have a question. So that's interesting. So you compute the normal gradient and then you compute the new coefficients, but then you update the coefficients, or you actually do the modification on the gradient itself?
We do the modification on the coefficients. So yeah, we update the coefficients with respect to this batch loss, you know, 100 training samples or something. And then we go and basically fix things to move them to be more monotonic.
Right.
And again, I'm not saying that this is the best way to handle these constraints in general, but with the TensorFlow library, we found this was the nicest way to handle it and use the TensorFlow library primitives that we had available and that people promised they were going to keep updating.
All right. Let me maybe check in Vienna if it's I don't.
There's a question in the chat actually.
In the chat, okay. All right. Should I read it out loud? So it's from
Yes, please do.
All right, so from Sasha. Well, Sasha, if you want to read it yourself, otherwise I'll do. So the question is, in modern ML, let's say deep neural networks, I think it's still hard to understand optimization and convergence due to using convex methods on non-convex problems, resulting in potentially different solutions obtained by pure SGD or something with momentum or additional tricks. When you additionally introduce some kind of prediction for handling constraints, do things get worse in regards to understanding what's happening here convergence-wise?
So it's a little hard to compare across like different function classes. So the studies that we've done with that are more based on these deep lattice networks where we're using the interpolated lookup tables. I would say in general, training time tends to be fairly similar. Adding constraints might make things about twice as slow. If you do it poorly, maybe 10 times as slow. The more constraints you add, the smaller your possible set. And so you do sort of naturally tend to get less churn. That is, if you train twice, you get solutions that are more similar or that act more similarly. Mm-hmm. And that's the other thing, right? Is you can have two models that maybe look very similar on test accuracy. As you say, you can train two neural nets and they might behave very similarly in terms of an aggregate metric like test accuracy, but they might change different numbers of decisions. So just because you're 90% accurate doesn't mean you're 90% accurate on the same training examples. And that can lead to a lot of problems, again, with the stability in these sort of big machine learning systems. So we haven't seen any problems. Generally, constraints, would help us with these issues. And while it's nice to train fast, when we worried a lot about optimization, it was always on the test side, and the evaluation speed was always much more important. That said, our training was never so slow that it was a huge problem. Usually I think our biggest models would take about a day to train, and everything was distributed nicely for these bigger models.
I think the question is also regarding to...
I'm not sure I did a very good job answering that question. I don't think I understood enough what you were looking for, other than, your convergence criteria, again, is going to depend on your loss and how you're doing the SGD and the momentum and stuff. And you'll get different, you'll fall into different local minima because of that. But with constraints, you're constraining which local minima you can fall into.
Yeah, maybe the question is also to hyperparameter optimization, that it can be sensitive to the hyperparameters that you choose, and that does it become even more difficult in this case or not, or are the learning curves very different for? Maybe it's in that range. I also didn't ask the question, so I can't be sure.
Yeah, from hyperparameter optimization, we studied that quite a bit, and we haven't seen that be as much of a problem as you would think. When you have like something that's acting as an ensemble, and a lot of neural networks are basically acting, you can roughly interpret them as ensembles as well. You get a lot of averaging. So even though you have like a bigger set of things, you maybe get more averaging. Whereas if you have a small enough set, things are sort of more constrained by the fact that you have fewer parameters. And so it's just sort of this mid-range where things get kind of noisy, and you tend to get more stable responses with either very large models or very small models. But it can depend a lot on the data and how crazy the data is.
All right. So I have one more question. So when you first were explaining the second type of constraint, it looked a bit like cost-sensitive learning, especially like the churn one. You could formulate it as a, I don't know, like traditionally as cost-sensitive, being that the examples, or for example, you had the example with the hand-labeled examples, right? So like a cost-sensitive approach would make these a lot more costly than the others. Do you think that the things that you propose can be derived back into costs on individual examples, or are there interactions that go beyond individual cost values per example, for instance?
So when I've worked in cost-sensitive learning, we were usually thinking about weights on like making positive errors or making false negatives versus false positive errors, or weights on different class errors. So that's a little different here, because here a lot of what we're talking about is looking at a slice of data. But as you say, you could have said, well, I've got this hand-labeled example set, and on that slice of data, I'm going to have 100 times penalty if I get it wrong. And I think this gets back to the question of, well, could I just penalize? But it's a little hard to know, what does it mean to have 100 times penalty on those training examples? And now someone goes and they get a different training set next week to go train on. Is that 100 times penalty still what you want? Or has the fact that they now have twice as much training data change that notion.
Right.
So from a semantic perspective, we just found it's easier and better to force people to write things more like as a constraint, that just stayed more stable over time and over the different changes that were happening. But often, yes, you can convert that, you can convert any one constraint into something that is a very similar story with a penalty.
All right. Any more questions? All right, so Maya, thank you very much for this excellent talk. I think the semantically interpretable argument is super strong and the results and the methods are very nice. So very glad that, that we could have this talk by you here. And so maybe we can mute our microphones and give a round of physical applause. Yeah. All right.
Okay, great. Thank you very much.
Yeah, so I'm happy for the organizers to interrupt me, but I believe that there is now a 15-minute coffee break. Can some of the organizers confirm?
Exactly. That is correct.
And so Maya, I don't know if you know, we also have this Discord server. You can see there's a website where people can ask questions on chat. I don't know, should you want to go onto that, feel free.
Okay, great. And people are also welcome to email me. Always get to hear from people who care about constraint optimization. Thanks.
All right, great, thanks. Bye.